Alright, Trinity Classical Academy. Excuse me. We are about to get spherical, y'all. So, buckle up. Math fans, here we go. We're on page 156. We're going to find the volume and the surface area of spheres. We're going to solve real world problems involving spheres. So a sphere is a ball, right? You're going to see that there's the area, or excuse me, the formula for the volume of a sphere given on page 156. Volume equals 4/3 pi r cubed. And there exists a video and I showed the video. The full proof of why that is involves a little bit of calculus, but it's very fun. You can see that little picture of a sphere. How they do a sphere is they kind of get a circular thing right here. They they put a belt around it, and then they continue the belt around the other side with some dotted lines to show that, hey, there exists space behind this thing, because we're dealing in three dimensions, which is why we cube it, because there are 3 dimensions. Fun times, you guys. So let's look at example 14. Find the volume of the sphere if the radius is given. The thing I like about this is there's only one missing component. We know what 4/3 equals. We know what pi equals. The radius is what varies with the sphere, and a sphere is great because it's all points on the surface are the same distance away from its radius. So we don't need to. There's no question, right? With like a pyramid, there's a question as to, well, what's the base shaped like? What's the slant height of one side or the other side, or things like that. It's a sphere is a sphere. There's really only one variable, and that's the radius. So an iron ball has a diameter of 6 centimeters. Find the volume of the iron ball to the nearest centimeter. Use 3.4 to approximate pi. Let's read what enthusiastic math student has to say. She is very excited about this math problem. She says the diameter of the iron ball is a segment that passes through the center and has its endpoints on the surface of the iron ball. The diameter goes from surface to surface straight through, and it passes the center. The diameter, just like a circle, half of the diameter is going to be the radius. The radius is the length of any point on its surface to the center. So this is this whole big thing is the d. That's where the d is. Half of it is the r. So we're going from a point on the surface through the center, straight through to the other point of the surface. So it says the diameter is 6. That means the radius is going to be half of that. So the radius is 3. So equipped with this knowledge is power, says the G.I. Joes. We plug this into our formula, right? So we're going to plug this into our formula, and we're just going to chug it away into our calculator. So we're going to find the volume equals 4/3 times pi, which they said to use 3.14, times the radius cubed. So how you punch this in on your calculator matters. And we're going to talk about this again with the next example in the next problem. But so you're going to do, there are really a number of different ways to do the keystrokes on your calculator, but what you're going to do is you're going to punch, I would do this, 4 divided by 3 equals, you're going to get an answer. It's going to look like 1.75. You're going to take that, you're going to do times 3.14. We're not going to use pi, we're going to use 3.14, so we get the same answer as the book. And you're going to do equals, and you're going to get a number, right? I suppose I can do it on my calculator and get a number too. So we'll go 3.14, 4 divided by, so you should get 4.18, and then a bunch of 6s. 6 repeating. 6 repeats. Pardon, I forgot to silence my phone before I began. But the answer can be saved in your memory. So you can take this jobby and then push memory plus. What this does is it says add this value to the memory. It's like hold that number. So it'll hold that number. It'll hold that number with the 6 repeating, which is the important part. So it completely holds this entire value in memory. Suppose that was unnecessary. Then you can go and take 3. You're going to punch in this little caret symbol. 3 caret 3. That means raise 3 to the power of 3. You could also multiply it out if you want to do 3 times 3 times 3. That's fine too. But if you take this, you'll get 27. You could also do that mental math in your head. 3 times 3 times 3 is 27. Then you take 27 and you do times. You're going to push this button, memory recall. That says bring up what the number that you're holding on to. Memory recall, so it'll bring up 4.18 and 6 repeating equals, and you should get about the answer that's shown in the book, which is 113 centimeters. Just to make sure I didn't tell you anything wrong, I'm going to go ahead and punch through these keystrokes. Let's see, 3 raised to the power of 3. My calculator actually has a cube button on it, so you can just oh, so on your calculator button might look like this too. Instead of the caret, it might look like x to the power of y. I know we covered this at the very beginning. You probably forgot how to use your calculator. That's fine and completely natural. Do not be alarmed. You can ask your parents. You can look at your instruction manual of your calculator. But one of these keys will be on your calculator. Should be something that looks like that. To my knowledge, I can't think of any other way that a calculator shows power. So like it works just like a plus sign, right? You do one number plus another number, one number raised to the power of another number. It works kind of like that, but it's usually buried somewhere on the side or on the top, or you might have to push the second function because some buttons have more than one function, so you might need to push second and then push the key that has that symbol on it, x to the y power or caret. Either way, hopefully you found it. If you didn't, you can, I guess, send me through Student Square a photograph of your calculator, and I will try to find it for you. Or ask your parents, or your co-teachers, or your friends, or your Google it. I don't know, however you want to find it. Sometimes Google has the best answer. You just Google, how do I raise a power on my TI, whatever, TI 23 BA2 Plus, whatever your calculator is. Google that exact phrase. It'll generally bring something up that's pretty reasonable. All right, that was a long explanation for this problem, but hopefully that reorients us to our calculators, gets us on the same page for really how to solve this problem. So I'm going to erasify this. Erasinate. And continue to erasinate. All right, we'll leave it like that. So we're going to pause and we're going to do guided practice number 1 on page 157. 157. Guided practice 1. Ready, set, go. Pause. Okay, great. Unpause. So it says the diameter of a sphere is 8.8. What is the volume of the sphere? Round your answer to the nearest hundredth and use 3.14 to approximate pi. Again, if the filling in every single blank really helps you out, great. If not, that's fine. Your answer should be approximately 356.64. It says round to the nearest hundredth, so you should have 0.64 cubic meters. That is one big sphere. That's big. All right, how do we do it? If you already know how to do it, if you got the correct answer, skip ahead. If you didn't, or if you want to watch me do it anyway because you enjoy that, I don't blame you. Here it's going to happen. So once again, they give us the diameter. So the diameter is 8.8, which means the radius is half of that, 4.4 meters. Which they kind of spell that out for you on that top of that problem. So we plug in the volume. Volume equals 4/3 times pi times the cube of the radius. We're going to need our calculators for this one. 4.4 cubed times 4/3 times pi. Another way you can do this, guys, keystrokes. If you do the cube first, that can be the easiest way to make sure you don't mess up on your keystrokes. You just type 4.4 times 4.4 times 4.4 times 4 divided by 3 times 3.14. If you just type that straight across, I bet you that'll work. I'm just going to confirm it. And indeed it does. You get 356.64 when you round to the nearest hundredth. So you can do that as your keystrokes. Another way you can do your keystrokes is 4.4 raised to the 3. Let's do that. (4.4) keystroke x to the y, keystroke 3. You might need to push keystroke equal to get a number there. And then you can say, okay, so it equals an answer, and then you do multiplied by 4. You can then do divide by 3. You might need to push the equal in between, depending on how your calculator likes to work. I think most of you have the Texas Instruments. I think it does just fine without pushing equals in between each operation, because it kind of does that standard notation arithmetic instead of reverse Polish notation. That's calculator geek speak, so don't worry about it if you don't have any idea what that means. But I think your calculator should be function fine without pushing equals. As soon as you push the next operator like this, it should automatically do the equals for you and then begin doing the next operation. Divided by 3, and then you do times, and then 3.14, and then you need to finish with an equals so you get your answer. All right. Again, if anyone is struggling with their calculators not behaving as they expect it to, reach out to me if you've exhausted all of the resources. I remember when we did this in class, it got interesting. It got interesting. All right, we're going to do example 15. So if you took the explanation off, please rejoin us. And then we're on example 15. I'm pretty much over my cold, so just a little stuffy now and then. So find the radius of a sphere if they give you the volume. This is going to be the same kind of algebra that we did where we work backwards from. They give us the left side of the equation, and we're supposed to find the missing piece of the right side of the equation. So once again, we're going to always start every problem by writing the formula out. It's good practice. It helps you to remember. And this example is going to really rock your calculator tools. Let me see if I can do something here. What just happened? Sweet, that's exactly what I hoped was going to happen. All right, we move this up to the top. Boom. Love it. I feel so powerful, like an evil dictator. I mean, benevolent dictator for the good of the people. Like, you know, King Henry or someone great. Frederick the Great. Maybe Mr. Bourgeois, the pretty okay. Example 15, find the radius of a sphere given its volume. Okay, so while on vacation, Mike buys a sphere of polished agate. Oh my gosh, if you guys ever get a polished agate sphere, those are amazing. I used to work at a rock store, but I won't tell you that story because we're talking about math right now. It's a gorgeous ball of crystal stuff. The volume of the sphere is 65.42 cubic inches. What is the radius of the sphere to the nearest tenth? Easy peasy, we got this. Use 3.14 to approximate your pi. The volume of the sphere, we start our work by copying that at the top of the page because that's just good practice because I said so. Next, we're going to plug in the values that we know. So our V equals 65.4. I'm going to try writing my things without lifting my finger up. 0.42 is approximately equal to 4/3 times 3.14 times r cubed. So I believe it should be pretty evident. I don't want to intersect with my sphere. Should be pretty evident what we do first, right? The approximately equal sign, don't freak out about that. Just treat it like a normal equal sign. Let's go ahead and just combine. There's a couple ways you could do it, but I'm gonna do it by combining this right now. So 4/3 times 3.14. Also, since this stays the same in just about every problem, if you memorize what this value happens to equal, you could just rewrite this value and I think I did this wrong. Did I do 1.75? My memory is treating me weirdly. Like, I feel like I wrote 1.75, and many of you are going to correct me and say, Mr. Bourgeois, 4 divided by 3 is not 1.75. It's 1.33. I don't know why I thought that. I think I thought that because I was thinking of 3/4. My brain inverted the 3 and the 4, and I was thinking, it's 1 whole, and then 3/4. No, it's not 3/4. It's 1 whole plus 1 extra third. Should be 1.33. All right, I'm not going to edit the video. I'm going to leave the mistake in there to be real and human, and because I'm too lazy to edit the video. But 4 divided by 3 is 1.33. Okay, so times 3.14 gives you 4.18 and 6 repeating. See, I know I got that. So this value is always a constant part of the equation. You could just leave it like that, and then r cubed. Until such time as they tell you to not approximate pi and to leave it in whole numbers, in which case then you have to go back to the original 4/3 pi. Anyway, you'll probably get very familiar with that number, 4.186 repeating. Then what we can do is we can divide both sides by this. One way that I can do that, since I already have, if on your calculator you already have 4.18, 6 repeating, just hit that reciprocate button. It looks like this. 1 over x. This reciprocate button will save you a step. It's pretty great, because then it turns 4.18, 6 repeating into its reciprocal, and then you just multiply it times this, times that number, and it's the same as dividing by that number, because dividing by any number is the same as multiplying by its reciprocal. So if you do 4.186 and you hit the reciprocal button, you get 0.23885350318471337579617834394904, I'm sure it goes on. But then you take that and you hit times 65.42 and you'll get the answer. Or you could just do it the long way if you want to, if that makes more sense to you, if that's easier on your not making a mistake. But the answer should be 15.62, we'll say 625, 62, we'll say 63. Is approximately equal to our r cubed. Okay, big old pause right here, you guys. Big old pause. If you're following along in the book, you should notice that it says to find the cube root of both sides. Look at what enthusiastic math student says. Use a calculator to find the cube root of 15.63. Enter the following: 15.63 caret parentheses 1 divided by 3 close parentheses. This is like a big, like, pay attention, guys. Wake up, everybody. Because this is how you do it. Like, so quick sidebar. What's the cube root of 64? The cube root of 64 is what times itself 3 times equals 64? The answer is 4. 4 times 4 is 16, times another 4. 16 times 4 is 64. So the cube root, remember, finds the product of 3 things. So on your doohickey, you're going to have 15. Why did it do that? I feel like Brooks is somehow messing with my touch screen again. No, I don't want that. No, stop. 15.63. If yours has a caret, do the caret. Mine has x to the power of y on it. X to the y. And then you can do parentheses 1 divided by 3, or 1 fraction 3. The other thing you can do is you can do 1/3, store that in your memory, 1 divided by 3, memory plus, and then do 15.63 raised to the power of memory recall. Anytime you do memory plus, guys, make sure you do MC, memory clear. This clears your memory. So whatever number you were holding from problem 3, you don't want that number to be screwing you up on problem 7. So memory clear erases the memory so you can start fresh. So we're going to do 1 divided by 3 close parentheses equals. The answer you should get is about 2.5, round to the nearest tenth. Okay, hopefully you're still with me. Pause, we're going to do guided practice number 2 on page 158. I love the reciprocate button on a calculator. It saves me so many seconds of keystroking. Oops. All right. 158, guided practice 2. All right. So unpause and all that, you got it done. The answer should be the radius of the spherical ball is about 7 centimeters. If you didn't get 7, or if you want to watch me do it anyway, go ahead and watch. Otherwise, you may skip ahead. So Diane bought a spherical ball made of quartz at a garage sale. The volume of the ball is 1,450 cubic centimeters. What's the radius of the ball to the nearest centimeter? Use 3.14. Okay. So again, we're going to start by writing our formula, which we did. So then they give us V. V is 1,450. Which equals 4/3 pi times 3.14, which is 4.186 repeating. That was awful. 4.186 repeating times our R cubed. We're going to divide both sides by that 4.186 repeating. I'm going to just hit the reciprocal button because I'm magical like that. Times 1450, we get 300. So divide both sides by 4.186. And we're going to get 346.34. So they just say to the nearest centimeter. They don't want us to round to tenths or anything like that. So I will leave my decimal in hundredths though. So we get 346.34. I'm struggling with these fours, man. I'm not used to writing like this. Is about equal to our R cubed. I'm going to raise this number. So I'm going to take the cube root. Cube root. Guys, if you have a key on your function that's like this, looks like that, or something like this, a root button, so like x to the root of y, that would be so much easier. Then you can just do it, you can just punch in your button, so x is always the first number. So then you could do 346.34 to the root, not square root, it should be the root, the xy root, x to the root of y, and then just push 3 and then equals. If you do that, you'll be you'll be cruising down easy street if you have that key on your calculator. Otherwise, you have to raise it to the power of 1/3, like the rest of us. Actually, it's very possible that my calculator somewhere has that feature on it, which is fine. Either way works, because they mean the same thing. So I'm going to raise that to the power of 1 divided by 3, close parentheses, equals 7.0226 and some change. So 7 centimeters was the rounded to the nearest doohickey jicky. All right. So hopefully you got that. If you are rejoining us, rejoin us. Play the video again. Here we go. So we're going to be moving past that weird, I mean, it's cool, but who has a hemisphere and a cylinder that just so happen to have the same radius? Not I. So I suppose I could make one or something. So find the surface area of a sphere. We're moving on to the surface area. This is going to be a new formula, which means I need to erase this. And also I need to move the page over. $159. And we're going to be doing surface area. Let's try that again. So this is, once again, it's the area of it's like a two-dimensional measurement of all of the coverage of the sphere. I have a really fun example. I'm just going to go ahead and share it because why not? My dad always used to get really frustrated when he would make spaghetti. So my dad would make spaghetti. Here's the spaghetti noodles. They're swirled in the pot, right? Spaghetti noodle is like a really, really long and skinny cylinder, right? And he would make a certain amount of sauce in the saucepan, and the sauce would go on the spaghetti. It would be red, and it would be wonderful. Many of you have a certain sauce ratio that you like. I personally like mine pretty doggone saucy. Like I need it to be, sauce is one of my favorite foods. I love sauce. And so like I want my tomato sauce to be enough that it completely covers the whole surface area of every strand of spaghetti. Like I want the spaghetti to be just slurpy, drippy, spattery with sauce all over the place. But the thing that would frustrate my dad was when he would put meatballs in it or vegetables, he'd put other stuff in it, like ground beef. Ground beef is a bunch of tiny little spheres. He'd put that green ground beef in there. We'd get sick because it was green. He'd put it in the spaghetti and suddenly there wasn't enough sauce. And he was like, I don't get it. Why is it that I always have one jar of sauce is plenty for the noodles unless I add ground beef to the sauce? Well, yeah, that's what he would do. He would add it straight to the sauce. He would add it into the sauce and make meat sauce. And then when you put the sauce into the noodles, it's like not enough sauce. He's like, did the sauce go away? Why is there not enough sauce to cover these noodles? And the answer to the question is surface area. When you add little tiny spheres to the pot, you've increased the surface area. So now you've got a lot of surface area for the same amount of sauce to cover. So we've got these little spheres of ground beef. We've got these long, skinny cylinders of noodles in the pot. And he was like, where is the sauce? The sauce, there's not enough sauce for these noodles anymore. Because, Dad, because there's more surface area. It's not just surface area of some cylinders anymore. It's surface area of cylinders plus spheres. And so that is a reasonable application of surface area. Another scientific application of surface area is, supposing you have hot soup, right? Some people like soup in a mug. It's very strange, I believe, but you have hot soup in a mug. It stays hot for a very long time. I like to eat soup out of these, they're called soup plates. They're like very shallow bowls. And I put my soup in a soup plate. Why do I put my soup in a soup plate? Because I don't like my soup to burn my mouth. I like to have my mouth intact so I can continue to taste food. One of these, you have surface area that is small. The cool air in the room is touching all of the surface area of my soup that is exposed to the air. So you consider the circle. This is just a flat circle that is exposed to air. Whereas over here, it's still a flat circle, but it's much bigger. It has a much bigger area. So the more surface area you have, the more it's exposed, the more the different temperature air is touching your stuff. Think about Dippin' Dots. Dippin' Dots melt faster than any other ice cream known to man because Dippin' Dots, instead of being one giant sphere, is a whole bunch of dinky little spheres. Dinky little spheres. The air touches more of the surface area, more of the surface of your ice cream. When you got all the instead of like one giant scoop of ice cream, you got a bunch of tiny little micro scoops of ice cream. And the warm summer air is touching your ice cream in more places when you have the same volume of ice cream that has greater surface area. All right, have I beaten that dead horse sufficiently? Surface area, it matters. It's especially for spherical things. It's got a lot of applications in science and in enjoyment of your soup and ice cream. So the formula is the surface area. I don't know why they gave it S. I would have done A personally, but they didn't ask me. 4 times pi times r squared. Why is it squared, guys? because we're dealing in 2 dimensions now. I said that the surface area is a 2-dimensional do-jobby. So we're going to have square centimeters, square miles. That's a gigantic sphere if we're talking about square miles. Maybe the whole moon or something. So notice I say this is a result that you will prove in a later course. If you were a part of the Zoom group, we ran out of things to talk about, so I showed a video about how to prove the volume of a sphere, that a sphere is just the same as a whole bunch of pyramids, skinny little pyramids put together. So there is a proof that exists to prove the surface area of a sphere equals 4 pi r squared. So pi r squared is the formula of a circle. Sphere is just 4 times that. Why is it 4? Well, you'll have to wait and see. So here's example 16. Example 16. A sphere has a radius of 3. What's the surface area? Use 3.14 as approximation for pi. Okay, we plug it in. So we have 4 times pi. They say the radius is 3. Oops, wrong tool. The radius is 3. 3 squared. 3 times 3 is 9. 9 times 4 times, and we'll give it its own space, times 3.14. We just plug that into our calculator, we'll get our surface area. 113.04 centimeters squared. Square centimeters. Turn the page, y'all. So 4 pi r squared, that's our formula. Because surface area is 2 dimensions, it's like circles and stuff. Even though I know it's a round ball, maybe it's hard to wrap your mind around. Haha, but that was really funny. You have to admit it. Admit it. It was funny. Wrap your mind around. We're talking about spheres and circumferences and surface areas of spheres. All right, whatever. Page 160. Do guided practice number 3. Do it right now. Do it. Do it now. Very cool. All right. So this one is a short one. I realized the last lesson was really long. This one's going to be relatively short. What is the surface area of a sphere with a radius of 6 centimeters? Radius of 6. Use 3.14 as an approximation. The answer is 452.16. You just plug in the numbers. You take 6 is the radius, 6 squared is 36. 36 times 3.14. Punch that in your calculator. Take that answer times 4 equals, you're done. You get 452.16. All right, example 17. Nope, I was right the first time. Example 17, find the radius of a sphere given its surface area. A tennis ball has a surface area of, holy simoleons, millimeters? Are you sure? 14,095.46 square millimeters. What is the radius of the tennis ball? Use 3.14 as an approximation for pi. Okay. Gigantic number is approximately equal to 4 times 3.14. So we're just working backwards like we always do. So start by writing your equation. Always do that. It's good practice. Did I mention that? I think I might have said it once. Good practice to rewrite your equation. So you wrote the equation S equals 4 pi r squared. They give us the S. I did it again. They give us the S. The S equals 14,095 and 0.46. When you're dealing with hundredths of a square millimeter, man, you are really precise. I don't even know if they're that precise manufacturing these things. Is approximately equal to 4 times the pi times our unknown squared value. Guys, we're going to divide both sides by 4 times 3.14. What was I trying to do there? 3.14 times 3.14. We're just going to divide that whole big thing. You do it on your calculator. 4 times 3.14 is 12.56. Reciprocate times 14,095.46 equals 1,122.25. 1122 and a quarter. Nope, we're going to slide down a bit. 1122 and a quarter is about equal to r squared. So, to take it home, we just find the square root. So take our answer that we have on our calculator, hit square root button, which you should have, which I should have. Do I not have square root? There we go, square root. Boom. Cool. 33.5. Hey, oh man, I wish I could show this in an easy way. So I've got this thing right here, and then the second function above it. I need more space. The second function above it on my calculator is the opposite, or the corollary square root. And then I've got this button over here that says x to the y. And then the second function above it, which is in a different color usually, is x to the root of y. And then you have this button over here that says second. When you push that button, then this button starts to do this operation instead. You see that? If you push second and then the button, it usually does its reverse. So a power becomes a root. That might be true on your calculator. Inspect and confirm or deny. Guys, pause it. Do guided practice number 4. Zip. And while I erase my board. Erasing the board, erasing the board, erasing the board, board. So Mr. West did not want to sing, huh? It's tragic, really. All right. We're doing GP4. The answer is 16 centimeters for the radius of that ball. If you want to see me solve it, here it comes. Otherwise, you can be done. You're done. Lesson over. Go home. I mean, you know. But here's the solution. Spherical rubber ball has a surface of 3,215.36 centimeters square centimeters. What's the radius of the rubber ball to the nearest centimeter? Use 3.14 as an approximation. The surface area, they give us the surface area. It's 3,215.36 equals 4 pi r squared. So we're going to divide the side by 4 pi, but it's going to be 4 pi times 3.14, our approximation. Let's see. Wake up, wake up. So it's 256 equals r squared. The square root of 256 equals straight up r. So it's 16 centimeters. All right, folks, reach out to me if you have questions about your questions. Otherwise, have a lovely weekend. I love you. Miss you. Bye.